Let us begin our amazing journey by asking the most basic question, which is what exactly is physics? Well, the most technical definition of what physics actually is would be that physics is the study of nature and its laws. And then what you do is you try to provide a mathematical model to describe its evolution and its behavior. So, since that was a pretty lengthy definition, so let me quickly write it down. So, physics is nothing but the study of nature and its laws. And then what you do is, and then providing a mathematical model to describe its behavior, to describe, by its I mean to describe a system's behavior. So, to describe a system's behavior and evolution. So that would be the most technical definition of what physics actually is. But that itself is a pretty complicated definition for someone who has just begun studying physics. So let me quickly break down what this definition actually means. So here, this definition says that physics is the study of nature and its laws. So this is a very basic assumption of physics that nature behaves or follows a certain set of rules or laws. By laws, I mean rules. Okay, so nature follows a certain set of rules, which we call laws. And I think the most famous of these would be the Newton's laws of motion, which kind of describes the motion of various bodies. That is, it tells us about the behavior, how the bodies under motion behave. And then we have Coulomb's law, which tells us how charges behave, or in fact, Coulomb's law describes how stationary charges behave, right? This tells us about how stationary charges behave. What about moving charges? Well, moving charges produce something known as electric current. Now, if you're not familiar with this term, do not break your head. I will explain these when I will be making videos about Coulomb's law and Biot-Savart's law. So, Biot-Savart's law kind of describes the behavior of moving charges, which produce the magnetic field. In fact, Biot-Savart's law and Coulomb's law do not completely describe the behavior of stationary charges and moving charges, but you will know that there is something known as the Maxwell's law, which describes the motion of all kinds of charges because it is not a single law. These are four different laws. And I will not tell you what the laws are because at this point you are not qualified to know that because you will not know. It's a very complicated concept. But Maxwell's law basically describes the behavior of charges in general. And then we have the Newton's law of gravitation. So we have Newton's law of gravitation, which describes the behavior of masses, right? How masses will behave or attract each other under certain conditions, or when they are at a certain distance apart, or when the masses have a certain magnitude. how are they going to behave? That is put forward by the Newton's law of gravitation, which is partially wrong. Newton's law of gravitation is not a completely correct theory. In fact, the most accurate theory of gravitation is actually Einstein's general theory of relativity. And then we have Einstein's special theory of relativity, which describes the motion or the behavior of fast moving particles. So, this describes the behavior of fast moving particles. That is, you're soon going to find out that Newton's laws of motion are actually wrong, partially wrong for bodies that move comparable to the speed of light. That is, by fast moving particles, I mean velocities or speeds, which is comparable, so speeds comparable to light. And how much is that? Well, we denote it with the symbol c. Why c? Because the speed of light is constant. When we will dive into the special theory of relativity, one of the most basic postulate would be that the speed of light is constant for all inertial reference frames. Again, don't break your head with this complicated concepts, which we are going to look into in more greater detail in our future videos. So the speed of light is denoted by c and its value is approximately 3 into 10 to the power 8 meters per second. So these are some of the laws, right? And then we have the quantum mechanics, the laws of quantum mechanics, which describes the microscopic world. So the laws of quantum mechanics describes the microscopic world. A microscopic world, I mean the world of atoms, the world of subatomic particles such as electrons and quarks, or the world of nucleons such as the neutrons and protons. In these kind of very small particles, the usual laws of Newton, the Newton's laws of motion, gravitation, or the Einstein's theory of general relativity, they all break down. In this world or this realm, of physics, we have to work with quantum mechanics. Quantum mechanics is the most accurate picture of this subatomic world. So these are some of the laws of physics, right? The laws according to which our universe works, and that is these are the laws which come in our technical definition of physics. And then once you have studied these laws, which might be provided by experiments, that is, sometimes these laws will be in the form of axioms and postulate. Once you have got these, then what you do is you try to provide a mathematical model to describe a system's behavior and evolution. That is the Newton's laws of motion, for example, if you take it, then just saying that a body remains in a state of rest or motion unless acted upon by an external force, or when you take the Newton's law of gravitation, just saying that force between two masses is proportional to the product of their masses and is inversely proportional to the square of the distance between them. It's just a pure English, but that is not how physics works because then it is philosophy, right? It would become philosophy. But physics tries to provide a mathematical model to describe a system's behavior. For example, if you consider the Newton's law of gravitation, then the mathematical model would be this. The force between or the gravitational force between two masses would be equal to minus, because the force is always attractive, G m1 m2 upon r squared. This is exactly the statement which I just told you in simple English, but here it is a mathematical statement. So here this is a mathematical statement. And this is what makes physics different from philosophy. In fact, the way I personally like to define physics, right, this is my personal definition of physics, is that I like to define physics as philosophy plus mathematics. Right? It is a philosophy plus mathematics. And without mathematics, you do not have any physics, or without philosophy, if you have only mathematics, then that is just mathematics. There is not physics. Only when you combine philosophy with a certain set of mathematics and then you prove it experimentally, do you say that you have a accurate model of a system? And that is exactly what is told over here, providing a mathematical model to describe a system's behavior and evolution. That is, if you consider the Newton's law of gravitation, then it tells you that if I have two masses, let's say this is a mass m1 and this is a mass m2, then they are going to attract each other with some gravitational force, F of g. And as you are going to find out in Newton's third law, this would be minus F of g. That is, they are going to be equal and opposite. It is known as the law of action and reaction. But more on this on my video on Newton's laws. So they are going to attract each other, and how they are going to attract each other is exactly that is the behavior, how these are going to behave. By the way, here we will have a unit vectors, but don't worry much about. So how those masses are going to behave, right, when kept at a certain distance apart, let's say they are distance r apart. So how those masses are going to behave is provided by this mathematical statement or this mathematical model, which was provided by Newton, that we call the Newton's law of gravitation. And then how these masses are going to be attracted towards each other, how they are going to accelerate, when are they going to collide, right? All this will be explained by Newton's laws and Newton's laws of motion and Newton's laws of gravitation. So that is what I mean by providing law mathematical model of systems. For example, the Coulomb's law. The Coulomb's law, just like the Newton's law of gravitation, will tell you how two charges are going to behave. When two charges are kept at, let's say, some distance r apart, I have kept a charge plus q and a charge minus q, then how are these charges going to behave? That would be explained by the Coulomb's law, right? But it only deals with stationary charges. If we have moving charges, then we have Biot-Savart's law coming in, because there is going to be current and all kinds of charges, stationary, moving, or let's say we have a charge which is in the form of a plane, or the charge which is in the form of a cylinder. Everything is described by the Maxwell's laws, which are actually mathematical laws. I'm not going to write down the Maxwell's laws right now because it will only end up you scratching your head. So I'm not going to do that. We are going to look into it when I make a video on the Maxwell's laws. This is, although this is a technical definition of physics, physicists like to go beyond this. Physicists like to provide models which are not directly observed in our everyday world, but might be correct. That is, they like to predict certain models of our universe, right? Physicists like to predict models. For example, when Newton gave his law of gravitation, what he observed was that he asked a very simple question. He observed an apple falling from a tree. So he asked, if an apple falls, does the moon also fall? Right, so these kind of laws are actually given or based upon observation, but there are certain models of which are beyond what we can observe in our everyday life. For example, Wolfgang Pauli had predicted the neutrino. We never observed a neutrino, but he predicted it because the beta decay was violating the conservation of energy, momentum, etc. So he said that there has to be some particle which conserves these quantities. So he predicted the neutrino even before it was observed. The very same way Paul Dirac predicted the antimatter, right? Even before it was discovered, because the math, when they tried to solve the math was pointing them towards these particles, that such a particle might exist. And there are still such models, For example, string theory predicts the existence of strings or membranes. So it says that every subatomic particle is made up of some tiny vibrating strings. So these kind of models go beyond our everyday observation. They might exist or they might not exist, but physicists like to predict such things. And another example of this would be the multiverse. There are two kinds of multiverses, one which exists in cosmology and one which exists in the medieval theory of quantum mechanics. Now, those were a pretty heavy concepts, and I do not want you to get very concerned with them because we are going to be least interested in them. We are going to be least interested in this section of physics. We are going to be more interested in this technical definition of physics first because we are not physics researchers. We are beginners in physics. So we'll be studying the laws of nature and then how we can provide various mathematical models which describes a system's behavior. Now, what you need to understand what I mean by a system. That is, a system isolates a certain section of the universe. A system isolates a certain section of the universe from the rest. For example, when I gave you the example of these two charges, here our universe is made up of a hell lot of charges, right? We have a lot of charges. But here we are concerned only with these two charges. And hence, this is what forms our system, right? It is only the part of the universe that we are concerned about. That is the part of the universe whose mathematical model we are trying to provide. That will constitute our system. Right, and these two charges form a separate system than these two masses. And that completes our understanding of what physics actually is and what we are going to study in this journey on my channel. First, we are going to begin with the mechanics. Then we are going to move on towards electrodynamics and the special theory of relativity. Then we are slowly going to move towards quantum mechanics. And then we are going to combine the special theory of relativity with electrodynamics. We are going to combine the special theory of relativity with quantum mechanics. Right. And slowly we are going to move towards this section of physics, right? We are going to move towards this modern section of physics or a more advanced section of physics. But for now, this is what physics is. That this is physics for you. If you enjoyed this video, do not forget to subscribe to my channel and like this video. I will see you in the next one with more such interesting concepts in physics. Thank you for watching.